Yoav Shoham, Professor Emeritus at Stanford University, Professor Emeritus of Computer Science, but more importantly for this episode, co-founder of a hot new startup called AI21 Labs. Welcome to the Data Exchange Podcast.
Great to be here.
So when you folks came out of stealth, I immediately heard about you and I went to the website. So I think the tagline at the time was the largest language model available to developers. I think that's still technically true. There might be larger models, but they're not necessarily available to developers. So first question, for those of us who are not into the business of training large language models, what gave you the confidence that you can train 175 billion parameter model? So what was the genesis of AI21?
All right, then I need to tell you, I need to go back 4 years, almost 4 years, 3.5 years. And actually the premise of the company didn't start with large language models. We sort of fell into that. It started with an observation of where AI is today. And I have the benefit of being really, really, really old. And so I remember AI back in the 80s, where the hoopla around AI was not dissimilar to the hoopla today. If you go to there's a website called AIindex.org.
Which you started, right?
That's right. That's at Stanford, and it's still going strong, and it puts out various things, but most notably annual reports about the state of AI. And you'll see many of the graphs are U-shaped, whether you're tracking the number of units taken at college, or the attendance in conferences, or VC money put into AI companies. They all were U-shaped. And back in the 80s, standing room only in conferences and so on. And then in the 90s, you couldn't admit you're doing AI, even if you were, what we call the AI winter. And of course now, my plumber is doing AI. Everybody's doing AI. But the subject matter, the focus was very different. Back in the 80s, the focus was on what we called knowledge representation and reasoning, sometimes called good old-fashioned AI. The paradigmatic example being sort of a so-called expert system. You go and interview a doctor, and you ask her, well, how do you diagnose a patient? And she says, well, I look at these symptoms and I ask these questions, I do these tests, and depending on what comes in, I do some more, and maybe a decision tree or something probabilistic. Machine learning didn't play an important role. Deep learning wasn't a thing. And there wasn't much data, there wasn't much compute, nor did you need much. It wasn't as terrible as some people sometimes think, but it certainly sort of overpromised. And then we went into this hiatus. And now it's the mirror image. And now all you have is endless data and infinite compute. And we do statistics at the scale we never imagined possible. And you give me the pixels, I show you the cats. You give me customer data, I do segmentation. And so we do pattern recognition in an amazing scale, and many, many problems lend themselves to that, but not everything does.
Right.
And so in vision, it's easiest to miss that, because in vision you have the problem of object recognition, which is so clearly defined and so obviously important. And so, a lot of work went into that, and ImageNet was solved away, and endless applications. You didn't see the same impact in language, because in language, nothing. So you see, object recognition is quote unquote easy. It's a very local problem. It lends itself to local methods like convolutional neural nets, CNNs, and in language, nothing is local. Everything is tied to everything else. The underlying semantics has to do with connection between words that are very intricate. And so for a long time, we didn't see that impact in language. And then we saw about roughly, give or take 5-6 years ago, where transformers started to take hold. And, an evolution, but maybe the two best known examples are BERT from Google and of course, GPT-3 from OpenAI. The former more geared towards natural language understanding, the latter more towards generation, but these are just rough categorizations. And suddenly they made a difference. You looked at the academic kind of benchmarks, and they suddenly got dominated
Right.
by the transformer-based methods. And so the feeling was that okay, problem solved. But then the answer is no.
But it's not right. I mean,
Right.
yeah. When you look at some of the responses of GPT-3, even right to certain prompts, right?
So whether you look at natural language understanding, even on the so-called solved problems, they show great brittleness. And if you change little parameters, you go out, change the distribution, go out of domain, put distractors, suddenly those good answers become nonsense, not better than random. And in generation, I don't know what to tell you. I mean, GPT-3 and its ilk are incredibly impressive, but it's always hit or miss, and often more miss than hit.
And that's why Yoav, even people, I don't know how serious people are, but they even now have a job title called prompt engineer. The maestro prompters of these days.
Right. Right. So prompt engineering is what feature engineering used to be machine learning, maybe 20 years ago.
Right.
And it's a natural evolution in the process. It's getting more codified and more algorithmic. So now there's actually prompt tuning and various algorithmic approaches to choosing good prompts. And as people are discovering, prompt tuning is also just a path in the road. But going back to this, where we started the company, our belief was and still is that large language models are necessary components of anything you do in natural language, but not sufficient. And if you take a simple sentence such as, your 5-year-old comes home and says, Danny hit me at school, so I hit him back, but the teacher only saw me hitting him, so she punished me, it's unfair. That's really something a 5-year-old easily understands, and no machine really can make sense of it in any sense of making sense. And when you think about it intuitively, how do we understand it? We understand there's a timeline, and there are events in time, they're connected temporally, but also causally, and there are agents with mental state. There are these actors who know things, others who don't. These guys know they don't. There's emotions, there's a sense of fairness, and all those abstractions, don't those emerge from the network? Now, it's surprising how much does emerge. So we need to be careful when we speak about networks. They've surprised us in the past, but nothing like what I've just said emerges. And when we started the company, it was based on the premise that if we want to make progress on a faster than an evolutionary timescale, we need to inject structured knowledge, semantics, priors into the networks. And this is exactly what AI did back in the 80s. And so we really wanted to take the good old kind of ideas of semantics from the 80s and merge them with modern day deep networks.
Let me ask you this. So if you're going to inject semantics and infuse knowledge, how come the language model? So do you expect then the language models over time will become less big? I mean, more manageable? More.
Good question.
Yeah.
Good question. I believe size will matter, will continue to matter.
Okay.
Now, whether we need to go from 200 billion to 2 trillion, I don't know. There are signs of.
But 200 billion, Yoav, 200 billion is still outside the realm of your average academic. You still have to have a lot of resources, right? So at the 200 billion.
It's very difficult. I can tell you that we have an unusually kind of capable team, not just on the algorithmics, but also on the engineering. And training a 200 billion parameter model is harder than training a tiny model of 2 billion. It's funny we speak about things small, but stuff happens at that scale. That's for sure true. By the way, so I have my good colleagues at Stanford, and we're very happy to collaborate with them. We're giving them access and credits on, so we built our own model.
Right.
We have amazing, respect for OpenAI, and but we felt we needed to build our own, and so we did. And we're happy
so
to.
your model, you folks label your model as accessible to developers, which it is. What about, is it open source?
No.
Oh.
We actually didn't set out to be a model provider. We really have our own application called WordTune, which
I'm a paid user.
Oh, I'm really happy. And you have many people who are are using it like you, and I have to say it's been very gratifying, the reception. And we built a whole bunch of tools, language models, and it doesn't end with language models. Lots of machine learning and optimization on top of the language models to power WordTune.
Oh wait, so what's the sequence of events? Did you build the language model and then come up with an application, or you had an application in mind and realized you had to build the language model?
It was actually more complicated than that. We started to build a whole bunch of technology, language models, and a whole bunch of things, basically coming up to speed, doing various prototypes. We had a toy system called Haim, which was like a GPT-2 at the time, but you'd give it not only a beginning but also an end, and you can interpolate between the two and tell stories. But these weren't products; they were just toys. So we're playing with technology, but we were committed to not just being a research lab. We really wanted to. So we asked ourselves, what is the problem that we can address that was a good match with our technological and scientific ambition? Because textual processing is everywhere, but not everywhere do you need the depth of it. And so we just set up to, so we defined the problem of redefining how we read and how we write. Because when you think about it, the way we write today is the way a product manager at Microsoft decided in 1980. Even if you write in GDocs and Gmail, it's fundamentally the same experience. And the way you read is the way Gutenberg decided in the 15th century with a printing press. Somebody put it on a piece of paper on a screen and we look at it. And we felt like there's really an opportunity to really rethink these two experiences and making them an AI first experience, not put as a feature, a smart compose or a spell checker, but really think about the machine as a thought partner in both experiences. And so we have a product vision, and WordTune is really a first leg in that product vision, which we find very exciting.
You mentioned something earlier that I want to drill down to a little bit, which you said size will still matter. So there's, 2 billion won't be enough. You might still have to go into the low hundreds. So is that because now I'm also starting to see people who are putting out smaller models. So there's actually one from Stanford, this retrieval-based neural model, where they have kind of like a search. Mate, who's a friend of mine. But what? In that particular retrieval-based neural model actually has phenomenal performance on some of these benchmarks, which, by the way, I want to ask you about these benchmarks as well, because for those of us who don't follow, there's confusing to follow those benchmarks. So first of all, size. So there's people who are trying to explore this kind of size dimension. Maybe we can get by with less size, but you seem to believe that there will still be a minimum size that.
Right. So the question, size will matter. In our opinion, does matter. What size is an open question.
Yeah.
It's also the case that depends for what. So just to finish the picture, so we built these models and we decided to make one of the models, namely Jurassic, available to developers. But we have a large model of 178 billion parameters, but we also have the small model of 7.5 billion parameters. And we actually encourage the people to use the small model. It's much more, it's cheaper and more efficient. It just costs money to generate all the tokens. And it's just cheaper to do it with the smaller model. And the truth is you can get incredibly good performance if you use the large model to generate training data and then fine-tune it to the small model.
I see.
And so we think that different size models have different roles. And when you actually go to production, you don't want to be serving from a 200 billion model.
Not from your phone.
Not even from AWS or GCP. It's just slow and expensive.
Right.
And so and so we think that small models, and you're right, there are all kinds of demonstrations where small models are can be incredibly useful if you fine-tune them to the task, and if you're really smart about your inferencing. So basically, the model is a distribution over a language, and the question is, how do you sample from distribution? And really, inferencing is an area that hasn't received, I think, as much attention as it deserves. And so I think just by being clever about the inferencing, you can get away with smaller models. So I think there's a ton of work here, and there'll be a role for large models because at the end they can generate distributions that small models can't. But there'll be a role for small models, especially as you specialize them to specific tasks.
That's interesting. So I've never heard of this kind of approach to tuning, which is basically you have this gigantic model, and then let's say you want to create a chatbot for a very specific area in medicine, some specialized area in cancer. Then you feed it a little bit of, feed the large model some training data, and then you use the smaller model in the end.
That's exactly the workflow we recommend to our users of using Jurassic, and it's a win-win.
How much training data do you think you need for this tuning step?
Rule of thumb is with 50 examples, we do great, but really depends on circumstances. We have some examples where we show that if you give us just 10 examples, this is for sort of text, kind of article classification task, benchmark that's out there. By using this workflow with 10 examples, you get to the performance with a large that's equivalent to the performance of the large is the small. The large is the new small. Large is 7.5 billion. The jumbo is 178 billion. So by boosting it with these artificial examples, with only 10 labeled examples, you get the equivalent of hundreds and hundreds, sometimes even 1,000 labeled examples on the jumbo. So it's a very powerful approach.
So I have a question about benchmarks, since you're also the maintainer of the AI index and also a former academic. So there's all sorts of these benchmarks, right? Like Squad and things like that. So how, and then Squad apparently has been already beaten by several teams, at least have exceeded human level accuracy, several teams, Baidu, Microsoft, and I forget who else. So are these benchmarks, are they the right instrument for progress in NLP? I guess, right? What else do we have?
It's a great question. And I think benchmarks are a double-edged sword. They do bring value. They do sort of focus attention, give you some measure of progress. And you're right.
People rally around them, right? So,
and there's a way to compare.
Yeah.
So, like you said, Squad 1.0 was solved quickly, and a year later, Squad 2.0, which added was also quote unquote solved. And then people spoke about glue and super glue, which is an amalgamation of different natural language understanding tasks. And they're also arguably the systems are beginning to approach, sometimes exceed human level of performance. But you need to take this with a grain of salt. First of all, the performance is very brittle. if you change a few things in the task, the performance can degrade dramatically, which means that I don't want to say that people cheated or studied to the test, but inadvertently you latch onto the statistics and the training and the data from which the training set is taken. And when you then go and try to use it in the real world, the task was very different, the distribution looks very different, so the systems don't perform well. And so you need to be careful how serious you take benchmarks. I can tell you that internally at AI21 Labs, we don't spend a lot of time on benchmarks. Sometimes we use them as training wheels. One of our first systems called SenseBERT, we actually showed against what is called word in context, which happened to be just the right setting in which to test our approach. But by and large, we're driven by fundamental bottlenecks we see in the process, and ultimately in the success of applications, our own application, and now also those of the users of Jurassic.
So what's the role of academia? I guess academia produces a lot of the papers in NLP still, but they cannot compete in this large language model realm, right? So what's the role of academia versus industry?
Another great question. Listen, I mean, in general, even before the age of large, expensive language models, there was a brain drain from academia to industry. Right. You saw this in vision, but not only in vision. And a lot of my colleagues at Stanford,
Stanford and Berkeley people are like spending 2 days a week, at big tech.
Berkeley, that's on the east. That's East Bay, right?
So when you talk to people in academia, I mean, they don't have the resources to compete, right?
So now there's this added issue that it actually takes a lot of, not only money, by the way, you're right, you said resources compute, money, but it's also, but compute was also engineering talent.
Yeah.
Like you said at the beginning, this is hard engineering. And so it's a good question. I know that my colleagues, so there's also the issue of availability of training data. And so my colleagues in academia, in particular at Stanford, were a main instigator of the Natural AI Infrastructure Initiative, which I think is a great thing, both data and compute. My colleagues at Stanford now are involved in an attempt to build maybe not a Jurassic scale, but large scale language models for experimentation. And I think, I have one leg in academia, one leg in industry, so I'm really sympathetic to this whole issue. So we at AI21 Labs are making an effort to support academics wherever we can. So we've just now agreed with our colleagues at Stanford to just give them a good budget to do the research and education, by the way, using Jurassic. I think many of the fortunate sort of industrial labs that do have access to are also trying to be good citizens. I think the big question, I think, is unanswered.
Yeah.
Because the old world in which all the good ideas came from academia and then industry picked it up and commercialized it, that's not today's world.
So let's look at it from the perspective of even the conferences, right? So NeurIPS, now more and more industry papers, but also actually I wanted to pick your brain because NeurIPS historically has had trends too, right? So there was the support vector machine people, then the Bayesian people, then now deep learning. But now it seems like deep learning is it, unless there's another school that can prove they can match some of these performance on these benchmarks, right? So that people will switch gears.
I think there's a growing recognition, even among the most passionate neural nets fanatics, that that it doesn't start and end with backprop. I mean, my favorite example. On the one hand, it's amazing that Jurassic or GPT-3 can do arithmetic. You know, who thought you'd give it two numbers and they can add them? And in fact, if you give them a one-digit number and a two-digit number, they do pretty well. Give them, 10-digit numbers, they're clueless. And this is the solution to it. It's called the HP calculator. We know how to do addition. and so the idea that we'll just let the neural net learn mathematics on its own,
or use reinforcement learning to learn everything from scratch, right? So.
Yes, exactly. So in some sense, if you're patient, it'll learn something. It'll learn a lot. In fact, it'll learn to generalize. Even once it's performed well, it continues to internally optimize its representation and increase its internal abstractions. And it'll learn stuff. Will it learn the piano axioms? Will it know basic arithmetic as well as a smart kid? Probably not. Not soon. And there's absolutely no reason not to give it that knowledge. That's a very simple example. So I think there are many people in the community who realize that one needs to augment the pure neural machinery with stuff. And there's an argument what that stuff is. And one of the buzzwords is, neurosymbolic programming, combining, like I said, the more symbolic reasoning with the neural machinery. What that means, is different people have different interpretations. We have our approach to this, and others have others. Some people do believe, like you said, that you need to embody the machine in the real world so it gets, reinforced by its actual performance. Certainly, there's an emphasis on multimodal learning. So then everybody's doing that now. It's not just text, it's not just images and text and sound and you name it. The jury's out, and it's a bet, but my own bet is that neural backprop and reinforcement learning are necessary components, but not sufficient. And you want to inject structured prior knowledge that would be a game changer.
So I have another kind of general machine learning question, but I'll make it concrete and ask it in the context of these large language models, which is basically large language models, as you describe, a lot of it has become kind of an engineering problem. So where are the theoretical computer scientists helping us understand how these things work? So what's your sense of how do these things actually work? Are they just memorizing everything they've read or what,
Good question. Well, you know what the role of theory is? The role of theory is to show that what works in practice works also in theory.
But what's our level of understanding of how these gigantic language models work? So you have a sense of their brittleness, right? So that's important. But beyond that, what do we know?
We don't know much. I don't know much. Let me at least say that. Listen, they clearly memorize, but they clearly also abstract because you are taking a high dimensional input and compressing it into low dimension. So by definition, you lose the information and abstracting. Now, what are you abstracting? I don't think anybody has a good handle. Now, people are beginning to touch small parts of the elephant with various, probing methods. And you see, something, here's a system that kind of understands this part of syntax. But it's a little bit like people are trying to understand the human brain and say, oh, this is the area that learns, language, or it's very crude. And there's
Or the psychologists who study how children acquire knowledge. Are there like are there conversations between those sorts of people and the people?
No, there definitely are. I'm not one of them, but there's definitely an intimate conversation between machine learning people and neuromodeling people with fMRI models and so on. It's not something that I do, but I was just making an analogy, saying that we have inklings of what the networks do, but not much more than inkling. And by the way, a disadvantage of injecting prior knowledge and structure into the network is that you introduce bias and you may lose generalizability. So you need to be careful about it. The advantage is the network maybe have a clue about what they're doing and be more reliable and, for example, do addition well. But they can also explain what they're doing, because if you tie it to stuff, units you understand, like numbers and the addition, operation, the system can actually tell you why 1 + 1 = 2, not because the weights was such and such. And so, again, I think it's a multifaceted question, but one way to get a handle on understanding the innards of the system is to put structure there that we understand.
What about things like creativity? Hard to measure, right? It does generate. It can generate fiction.
Well, I'll up the ante. I used to give a seminar at Stanford, and then I also gave a TED talk on it called "Can Computers Think? Can They Feel?" I would start the course asking 6 questions. Can computers, let me see if I remember it, can computers think? Can they understand? Can they be creative? Can they have feelings? Can they have free will? And can they be conscious? And it's interesting, I would poll the students. These would usually be freshmen, so actually smart kids, before we ruined them. Yeah. And so I'd ask these questions before we started the course, and I'd record the answers, and then we go through the semester and then learn about AI and look about what these properties mean in humans, not just in machines. And then I'd ask the question again, and invariably people were first less sure of themselves, but also much more generous to computers. Now, going back to creativity, the initial reaction is, machines can't be creative, of course. And when you think about it, number one, it's not at all obvious they can't. And number two, it's not at all obvious what creativity is.
Exactly. Yeah. I mean, actually, even so even a much more specific task like summarization. It's hard to come up with. I mean, what's the gold standard data set, right? That you're going to use, right?
So going back to benchmarks and evaluation methods, that's a big issue in natural language. In understanding, and summarization, goes into that camp, and in generation also, and summarization goes into that camp also. There are various scores, as in machine translation also, and blue scores and so on, and they're not very good at all. And I can tell you that it's something that we spend a lot of time on, not trying to come up with general purpose yardsticks, but looking at the tasks that we're after and creating a yardstick that we believe captures well what we're trying to do, and then having a data set to match it and working against that. But it's an unsolved problem in the field.
By the way, I've done a couple of surveys for NLP, the applied NLP community, and one of the things people always cite as one of their bottlenecks or key challenges is what you described earlier, which is tuning, right? So I have a model that I don't know, it's in the cloud, but I have to tune it to my very specific domain. So actually, it was interesting to hear you talk about taking this gigantic, large model and then going to a slightly less big model and go to tune the model that way. So another area that these applied NLP people seem to be excited about is transfer learning. So I don't know to what extent are you guys at AI21 Labs are thinking about that too, or so what are your thoughts on transfer learning in NLP?
Yeah, I want to be modest here. I mean, people have used the term transfer learning for a long time, and I think people have strong intuitions and different senses of what that means. But certainly, you want generalizability, and you want what you've learned from a given domain and a given distribution to apply more broadly. Now, the question: what does it mean more broadly? You know.
So this is where people are trying to develop some tools to make that more concrete.
I don't think I have anything intelligent to say about that. I think
I
think it's a philosophy we subscribe to, but I don't know that transfer learning is one thing that lends itself to a precise definition. And then once you've mastered it, you go to transfer learning. But maybe other people have different opinions.
So what's your sense of multimodal systems? Are they're showing a lot of promise?
Yeah, for sure. I think, in an image is worth 1,000 words, and so on. There's no question that, it's not multimodal, but even take, coding, sort of computer code and documentation, and learning the code and the documentation simultaneously. There's sort of, you can think of it as multimodal. One is from the language of code, one is the language of words, of English, and you're learning them together, and they actually mutually reinforce. And so certainly, training on images and words together, or other modalities, has a lot of power for sure.
By the way, it's interesting you bring that up because GPT-3, one of the first manifestations is this coding assistant, right? So the GitHub Copilot.
Right, Copilot and now Codex.
Which a lot of people use. Which a lot of people use mostly as an aid, right? So.
I think the jury's out. Again, it's one of those things that it's surprising how well it does, but it's not clear it does well enough to be good for production purposes.
I only want I want the training set to be composed of code written by Jeff Dean and the like.
Right.
Because if it's the entire of GitHub, there's a lot of noise there, right? So.
Well, I think Jeff wrote most of GitHub anyway, so that's okay.
When it's trying to learn from a huge population where the quality is not clear, maybe they weigh it in the training. I don't know, but
no, I have to tell you, we've actually had good success with auto-generated code. We have customers who are using Jurassic in that area.
Really?
Now again, and Jurassic itself was, if you look at we actually published it, but it was actually, it was comparable to GPT-3 if you look at the jumbo version, slightly better if you looked at the large version than the comparable, 6.7, Curie model of GPT-3. But in code, it did much better. Jurassic did, just because of how we trained and what we trained on. But obviously once they did Copilot and Codex, they optimized for that. So it's surprisingly good. But like with everything, this is not fire and forget. You're much better off using it, but then you need to add stuff to it, like we did in WordTune.
Yeah, exactly.
WordTune,
WordTune is a great assistant.
right? And
Yeah.
honestly, it's a magical experience sometimes because it doesn't like change words or change the sentence in a local way. It gives you radically different ways of saying things, and often the experience is, oh, actually, this is what I wanted to say. It kind of
Yeah,
gets in
yeah,
your thoughts.
yeah, exactly.
But but to do that, it's like with generating code. Yeah, you start with a language model, but that's maybe a quarter of the work. Then the hard work begins of actually fine tuning and doing optimization and reweighting and pruning and various things, so you actually get to a system that actually does the work. And by the way, doing all this efficiently, so it's actually a pleasant user experience. That's another big challenge. So with code generation, it's the same thing. It's amazing what the language models do once you've trained them to understand code, and then you need to work hard.
So your models are in the 170, 180 billion parameter range. So what are your folks' plans moving forward? So are you going for the much larger, or what, or you're going to go the kind of the more as you describe it, kind of the combination of a large model with something else? So what's the
What I can say is we believe in brain and brawn.
yeah.
So we think that large models will continue to be important, like I said, but we think they can be much, much smarter than they are today. So Jurassic 1 was really a baseline model for us to reach parity with GPT-3 and be a workhorse for us internally. But we think there are more interesting things that to be done in language models. And many of our colleagues in the various labs in industry and in academia, are pursuing various avenues, and we are also. And I hope we're able to demonstrate interesting models that will be not just bigger but also smarter.
So what's your advice to someone who wants to get a PhD in NLP? Just forget it. Just go to work for big tech.
No, I'm a big believer in learning useless stuff. Somebody said that one of the advantages of going to university is that you're forced to learn stuff you don't care about and be really good at it. And it's amazing what you think is not useful will come back and be useful in settings you didn't anticipate. So I really and you'll get fundamentals that are, I think, really important. So I strongly encourage smart guys and gals to go and spend a few years to really do hard stuff and publish stuff, and that'll serve them well no matter what career they decide.
And with that, thank you, Yoav.
Thanks for having me.